So in this lecture I am going to discuss some problems based on pipelining and parallel processing for low power. So starting with a 3-tab FIR filter given by equation yn is equal to a of xn plus b of xn minus 1 plus c of xn minus 2, represented by its data broadcast structure, is fine grained pipeline, and this multiplier unit is divided into two smaller multiplier unit, m1 and m2, separated by a delay element. Okay, so this is the concept of fine grained pipelining. Now the given parameters are supply voltage for non-pipeline filter is 5 volt, threshold voltage 0.6 volt. This is for CMOS technology that we are going to use. Computation time of multiplier is 10 unit time, this multiplier. Computation time of adder is 2 unit time, and the computation time of smaller multiplier TM1 and TM2 is 6 unit time, 4 unit time. Okay, and capacitance of multiplier is 5 times capacitance of adder. And you have to calculate the voltage of pipeline filter and power reduction factor. So you have to find beta to calculate this two factor. So supply voltage of pipeline filter is beta V naught and power reduction factor is beta square. Okay, so the first step is to calculate propagation delay TPD. TPD for sequential circuit and TPD for pipeline circuit. Okay, so this is given by formula C critical path divided by K V naught minus Vt whole square to V naught. Okay, and critical path for pipeline filter is, let's say, C prime. Supply voltage is beta V naught and K into beta V naught minus Vt whole square. Okay, so why we are doing this? Because TPD will be equal to T clock, that in turn will be equal to T sampling. Okay, so propagation delay will be equal to clock period, that in turn will be equal to sampling period. And power reduction is achieved when sampling rate of both the systems is same. Okay, so for this you have to first evaluate this and then you have to equate this. So CCP is capacitance of critical path of sequential circuit, and C prime CP is capacitance of critical path of pipeline circuit. Okay, so critical path for this circuit is this one. Okay, a multiplier followed by adder, or this one, both are same. So this is equal to CA plus CP, and also it is given that capacitance of multiplier is 5 times capacitance of adder. So CA is capacitance of adder and CP is capacitance of multiplier and Cm, and Cm is 5 times Cu. So CCP becomes Ca plus Cm, and it is 6 Cu. And substituting this value to this equation, we have TPD sequential is equal to 6 Ca into V naught divided by K times V naught minus Vt whole square. Okay, now we have to find C prime Cp. So you have to refer this circuit. So this is the critical path. Okay, 4 unit time for this multiplier and 2 unit time for this adder. So 6 plus 4 plus 2 is 6, and also the computation time of this single multiplier is 6. Okay, so you have to choose either the sum of computation time of these two elements or this, whatever is maximum. Okay, so maximum of Tm1 or Tm2 plus Ta1. So for both the cases critical path time is 6. So now critical path capacitance is C of M2 plus C of adder. So one more information is given that Cm2 is equal to 2 times Ca and Cm1 is equal to 3 times Ca. Okay, so substituting this in this equation, 2Ca plus Ca is 3Ca, and TPD pipeline is given by 3 times Ca beta V naught by delta K into V naught minus Vt whole square. Okay, so now you have to equate TPD pipeline and TPD sequential, because sampling rate should be same. So this is 3 Ca V naught divided by K. There is also beta V naught minus Vt whole square, and it is 6 Ca V naught divided by K times V naught minus Vt whole square. So you can cancel out the common terms, and the equation will be V naught minus Vt whole square, that is equal to 2 beta V naught minus Vt whole square. So V naught is 5, Vt is 0.6, and beta is unknown. Okay, so you have to expand this and you will get this equation: 50 beta square minus 31.36 beta plus 0.72 equal to 0. So you have to solve this quadratic equation for beta. So you will get two values of beta. So two values are 0.6033 and 0.0239. Okay. So supply voltage of pipeline circuit is beta V naught. Okay, and this beta V naught should be greater than Vt. If this beta V naught is less than Vt, the circuit will be in off state always. So it is obvious that beta V naught should be greater than Vt. This is the selection criteria for beta. So if you select this as beta, it is obvious that beta V naught will be less than Vt. Okay, 5 into this term is less than 0.6. So obviously you have to select this value. So beta is 0.06033 and beta V naught is into 5. So this is 3.0165 volt. So you can reduce the supply voltage of the pipeline circuit to 3 volt from 5 volt. And this is the first thing that you have to calculate, and second thing is power reduction factor, that is beta square. So you have to simply square this 0.6033 square, and to obtain the value in percentage you can multiply this in 100. You can multiply this with 100. So this is a percentage value. Okay, so this is 36.4%. So coming to second example, a 4 tap FIR filter given by equation yn is equal to h0 xn plus h1 xn minus 1 plus h2 xn minus 2 plus h3 xn minus 3, and its block diagram representation is given, and following parameters are given. The supply voltage is 3.3 volt, the device threshold voltage is 0.45 volt, computation time of multiplier is 8 unit time, computation time of adder is 1 unit time, capacitance of adder is Ca and capacitance of multiplier is Cm, and Cm is equal to 8 Ca. So capacitance of multiplier is equal to 8 times Ca, and the sample period at which the system is being operated is 9 unit time, and its two level parallel version is shown, and the sampling period of this architecture is also 9 unit time. This means that the sequential circuit and the two level parallel circuits are being operated at same sampling rate. Okay, and if you do that, then you can reduce the supply voltage of this architecture, and by doing that you can reduce the power consumption of this circuit. Okay, so what you have to find, you have to find supply voltage of this circuit, that is beta V naught, and power reduction factor, that is beta square into 100%. Okay, so condition is given that both the systems are being operated at same sampling rate. So for this you have to again follow the same steps. You have to find propagation delay for sequential circuit given by C Cp into V naught divided by K into V naught minus Vt whole square. Okay, and similarly you have to find TPD for parallel circuit. So let the capacitance of critical path is C prime Cp beta V naught into K into naught minus Vt whole square. So CCP is given by the addition of capacitance of multiplier and adder. Okay, so this is the critical path. This or this also, both are same. So CCP is Cm plus C. CCP is Cm plus C, and Cm is 8 times C. So this is 8 Ca plus Ca. This is 9 Ca. And C prime Cp will be calculated from this architecture. So critical path of this architecture is this one, or it can be this one. Okay, so this is a multiplier followed by 2 adder. So C prime Cp is multiplier followed by 2 adder. So 8 Ca plus 2 Ca. This is 10 Ca. Okay, so TPD sequential is 9 Ca into V naught K times V naught minus Vt whole square, and TPD parallel is 10 Ca into beta V naught divided by K times beta V naught minus Vt whole square. Okay, so in this case you cannot simply equate this to equation, because for sequential circuit T sampling is equal to T clock is equal to TPD. Okay, but for this circuit this is not the case. TPD is equal to T clock, and T clock is equal to L times T sampling, where L is the number of parallel blocks that you are using. Okay, so T sampling in this case is TPD parallel by L. Okay, so you can increase the clock period for the parallel architecture, and you can increase it by L times of sampling period. So you have to equate TPD of sequential circuit with TPD of parallel circuit divided by L. So because you have to keep their sampling rate same, so T sampling of sequential is T sampling of parallel, that is 9 unit time. It is given, already given, and even if this is not given, for power reduction this two should be same. Okay, so equating this two values, this is 9 Ca 9 Ca into V naught divided by K times V naught minus Vt whole square, and this T C prime Cp is 10 Ca. So this is 10 Ca into beta V naught divided by k times beta v naught minus vt whole square, and level of parallelism is 2, so divided by 1 by 2. Okay, so cancelling the common terms, the equation will be 5 beta v naught minus bt whole square and 9 into beta v naught minus vt whole square. Okay, so 5 beta v naught is given 3.3 and vt is 0.45. So 3.3 minus 0.45 whole square, and on right hand side beta is unknown. Expanding this equation, you will get 98.01 beta square minus 67.3425 beta plus 1.8225 equal to 0. And solving this quadratic equation, you will get beta equal to 0.6589 and 0.0282. So beta v naught should be greater than vt, and for this beta will be 0.6589 and beta v naught is 6589 into 3.3, that is equal to 2.17437 volt. This is supply voltage of two parallel 5R filter, and you have to also calculate power reduction factor. It is simply beta square multiplied by 100%. So this is 0.6589 square into 100. This is 43.41%. So the supply voltage can be reduced from 3.3 volt to 2.17 volt, and by doing this the power saving will be 43.41%.